Hello everyone, this is Sabre, the Smart Circuit Breaker team. My name is Eli, an electrical engineer, and
I'm Carter, I'm a computer engineer.
I'm David, I'm a computer engineer.
I'm Emmanuel, and I'm an electrical engineer.
So, what is the Sabre Smart Breaker? The Sabre Smart Breaker looks to innovate on the conventional residential circuit breaker by incorporating solid-state tripping mechanisms, current and thermal monitoring, Internet of Things connectivity, and an intuitive user interface all into a compact, self-contained unit. This innovative design allows for easy replacement with standard name brand circuit breaker boxes, something that current market offerings fail to do. This particular iteration operates at 25 volts AC and features an adjustable current threshold that caps at 5 amps.
Test by Dr. Kunzu Soon from the University of Central Florida on behalf of Grid Interactive Things, the team looked to design a smart circuit breaker that can precisely measure current and temperature data that is transmitted remotely. Existing products in the market often feature non-standard designs and necessitate the installation of proprietary breaker boxes alongside individual breakers, significantly increasing the cost of upgrading to smart grid technology. The Sabre Smart Breaker addresses this issue by being designed to fit into standard breaker boxes. Furthermore, each breaker can be linked to user accounts on an online dashboard, enabling remote monitoring and control of each individual unit with minimal latency.
The team undertook this project because the issue aligned well with the individual expertise and backgrounds of our members, encompassing areas such as power delivery, signal processing, PCB design, embedded system, and full-stack web development.
After creating the rough outline of what was needed, the team collectively researched components that satisfied these requirements. For measuring current, the team came upon an ACS712 Hall-effect sensor, which outputs an analog voltage value proportional to the current passing through it. For measuring temperature, the team opted for the MCP9-700, which, like the Hall-effect sensor, outputs an analog voltage proportional to the measured temperature, and placed it directly alongside the main signal trace.
To optimize space, the team chose a compact 1.9-inch TFT LCD display that interfaces directly with the microcontroller using the S.A.B.R.E communication protocol, allowing it to fit seamlessly on the front of the circuit breaker. The team decided on a solid-state based mechanic for stripping the main signal line, due to its small footprint in implementation and microsecond architecture, and centered our focus around the TLP3547 solid-state relay, which is a photocoupled relay that can toggle the continuity between its two terminals based on a small current engaging an infrared LED.
at the core of the design is the ESP32 microcontroller, which features a maximum clock speed of 200 MHz, dual cores, and integrated Wi-Fi capabilities. To power the embedded components, we developed a voltage rectifier and regulator based on the LM2576, which converts an AC voltage signal to DC using a full bridge rectifier, and subsequently reduce the voltage to 5 volts efficiently.
The PCB design features 4 distinct custom PCB boards, each dedicated to specific components based on their functionality. The ESP32 is housed on its own board, equipped with exposed headers that facilitate connections and communications with the peripherals located on the other PCBs. The current sensor, temperature sensor, and solid-state relay were assigned to the second PCB, which also facilitates the passage of the main signal line. This configuration enables the essential data to be monitored and collected prior to being sent to the connected load. For the LCD display, it was given its own PCB that included the necessary passive components to power and communicate with it, as well as the 30-pin ribbon connector that actually connects to the LCD itself. Finally, the voltage rectifier and regulator was delineated onto the last PCB, which provides the appropriate power to all of the previously mentioned embedded components. All of the PCBs were designed to minimize the space occupied in accordance to the dimensions of a 2-pole square D circuit breaker, which is what was used as a basis for the 3D model.
The accompanying web application designed for remote monitoring and control utilizes the MERN stack, which integrates MongoDB for managing user and device information as well as historical logs. The back-end and middleware functionalities are powered by Node.js and Express.js, while the front-end is developed using React, allowing for the creation of reusable UI components. In addition, the front-end utilizes the Mantine component library, which provides a plethora of React components for implementing modern and interactive UI elements. Communication between individual devices and the server is done over WebSocket connections, which is done to provide direct streaming of telemetry data and from the server, while allowing the necessary overhead that comes with utilizing REST API protocols.
The team's initial focus during testing was on establishing the necessary circuitry for the power supply, which included both the rectification stage and voltage regulation stage. The rectification stage was crucial, as conventional voltage regulators require a DC signal for effective regulation, and as well the embedded components within the smart breaker also necessitate a DC power source. The circuit was initially designed around the LM5180 flyback controller, which, despite its ability to regulate the voltage, caused unexpected brownouts, i.e. voltage drops, occurring when the current draw exceeded a specific threshold, even though the design accounted for adequate current capacity. Consequently, the team opted for the LM2576 buck switching regulator, which offered a more straightforward and dependable circuit solution. This regulator was assembled on a perf board and underwent testing prior to its integration onto the final PCB, with tests involving continuous voltage monitoring over 10-minute intervals while varying the load from 0 amps to 2 amps. The Hall effect sensor, intended for current monitoring, was initially assessed without any load to verify that the quiescent output voltage was approximately the supply voltage divided by 2, as indicated in the datasheet. Subsequently, a known DC voltage was introduced in series with a 100k ohm potentiometer to adjust the current dynamically, allowing for an evaluation of whether the output voltage changed accurately reflecting the current flowing through the sensor. Following this, an AC signal was applied alongside a high wattage resistive load to examine the expected fluctuations around the quiescent midpoint voltage.
The implementation of the LCD was initially evaluated using a breakout board module that featured the same SPI-based display selected for the final design. This evaluation involved connecting the breakout board according to the SPI protocol and employing generic graphics libraries and functions from the ADF root to verify the display's functionality.
Upon completion of the system integration testing, a 3D model was created based on the dimensions of a 2-pole square D circuit breaker. As we mentioned before, was then 3D printed using PETG filaments. Each printed chamber was designed to accommodate individual PCBs, with the exception of the LCD driver, which was fixed to the rear of the front cover to facilitate a proper connection to the LCD screen through a ribbon cable. The design incorporates existing screw terminals and mounting clips from a conventional circuit breaker, allowing for direct installation into a Square D branded circuit breaker box. In future iterations, without the senior design safety standards constraints, the team aims to take the design further by scaling up the operating threshold to those modeling standard residential breakers, specifically 120 volts between 15 to 20 amps. The physical dimension of the breaker will be further minimized, potentially allowing it to fit into the single port breaker slot. In addition, relocating the screw terminals for the load to the bottom of the breaker will mitigate the risk of user contact while toggling the breaker. Although this concern is less significant at lower voltage, a main voltage accidental contact with both terminals could create a serious shock hazard. Furthermore, developing a mobile app to complement the web application will provide users with more convenient access to the system.